Welcome to Proterozoic history. This is a very critical time in Precambrian history, and it's the area that we have the most record of in geologic rock records since. For example, this is rock stacked up sandstone, to be exact, a Grinnell Formation from Glacier National Park, which indicates that this area was a tidal flat zone back in the Precambrian. There's so many clues to this that we'll look at, because embedded in these formations are also stromatolites that need shallow marine environments in order to live. There are mud cracks, there are ripple marks throughout this formation, indicating that Glacier, Montana, or Glacier National Park, which is in Montana, hasn't always been a glaciated neighborhood. So Proterozoic is an important part of our history that we're fixing to learn about. It lasts from 2.5 billion years to 542 million years. So much happened during this time. The evolutionary style of how we're going to crank out crust is going to change, and it's distinctive between Archean and Proterozoic. The greenstone belts were still being formed at the beginning of the Proterozoic, but at much slower rates. So the belts should be closer together in parallel lines for Archean and spread further apart for Proterozoic. Proterozoic contains sedimentary rocks associated with passive continental margins, meaning we didn't have massive orogenies occurring at that time, especially in North America. When you look at the span of time, we need to subdivide the Proterozoic into Paleoproterozoic, Mesoproterozoic, and Neoproterozoic. Those would be your eras. These are going to be your periods. And I'm going to tell you there's one that's super important too, actually, Cryogenian, and this top one that we'll be getting to a little bit later, because the top one represents the first development of widespread multicellular life. So lots of things are really going to happen in terms of what's going to occur from Paleoproterozoic all the way through Neoproterozoic, and we'll look at it because each one of these segments of time has a little story to tell that's very important to the overall scheme. The evolutionary of large land masses during the Proterozoic make up Greenland, North America, parts of Scotland, and even parts of Scandinavia. But somewhere between 2.0 and 1.8 billion years ago, several orogens, which are deformation belts we call the mountain building events orogenies, these orogens cooled and formed plutons that form much of our land mass that we call continents today, such as Greenland, Canada, and north central United States. An example of some of this material might be rocks that you would see in the core of the Grand Canyon, where Laurentia was being made. Those are that time frame of age, which would be like the Vishnu schist, which is the famous rock layer that's the core of very large mountains that existed back when this area was made. Which brings me to an important concept about the Proterozoic. Rodinia is the first supercontinent that was thought to have formed in the Earth's history, one that we do have some evidence of. About 1.1 billion years ago, Laurentia became a part of a supercontinent known as Rodinia. Somewhat of 75% of all continental masses present today existed as Rodinia, so we have actually gained land mass since this part of the Proterozoic. So somewhere during the Proterozoic, towards the late Proterozoic, we're going to start to see Rodinia come to be. It's considered to be Neoproterozoic in age, and that's important because a lot of our rocks where we find big igneous complexes like granites are considered to be Neoproterozoic in age. I can give you a handful of examples. The stuff that's at the Grand Canyon, there's some granites that date back to about that far. There is some granites in Texas by the name of Enchanted Rock, otherwise known as the Llano Uplift. There's some famous rocks out in Arizona that are Precambrian in age that are granites and that type of rock. You'll even find them in the Black Hills. They have some very similar commonalities, chemistry and texture characteristics that were the same that existed during this time frame. Rodinia broke apart by rifting, and this would be the first major indication that continents pull apart. We think that this rifting occurred and actually triggered the snowball Earth, which would have been the Earth's biggest glacial moment in the history of its entire existence, somewhere around 700 million years ago. So snowball Earth is going to basically create the most impressive ice age that we've had to date, including oceans and continents for the most part. Another important event that happened in the Proterozoic was the recognition of the first Wilson cycle. Wilson cycle involves a famous guy by the name of J. Wilson that you learned about in physical. He is considered the father of hotspots. J. Wilson recognized that as hotspots come out in the ocean, they create mid-oceanic ridges, which subsequently moves things like island arcs and ocean plates closer to continents, and then subduction will occur. So over time, you can close up an ocean basin and reopen it with rifting or vice versa. So when you open and close an ocean basin, its full cycle, with passive continental margins on both sides, that's creating a what we call a Wilson cycle. So rifting opens an ocean basin and it closes because subduction zone and island arcs form on both sides of the continent, causing the continent collisions to occur. When this does, it'll ultimately close off an ocean basin. And again, we can reopen an ocean basin simply by the process of rifting apart a continental mass. So that is an important element to understand. Wilson cycles have first been documented in the Proterozoic, and we've seen them since. Stromatolites began to be very common somewhere around 2.3 billion years ago during the Paleo-Proterozoic. It's important because as they continue to crank out oxygen, they're going to oxygenate the ocean, which is going to fill the oceans as oxygen gets in there and cause any kind of iron to precipitate out and drop to the bottom of the ocean floor. So they're very instrumental in forming thick iron layers known as banded iron formations. That's why so many of them exist in Paleoproterozoic rocks as compared to Archean, and why we don't find them in younger rocks after the oceans have been saturated with oxygen. So when we start to find oxygen in the air, that's going to lead to the first presence of continental red beds. 92% of all banded iron formations were deposited in the early Paleoproterozoic, somewhere between 2.5 and 2.0 billion years ago. So pretty much like almost all of our steel reserves on the planet are made from this time frame right here. And banded iron formations, this is one I brought back from Australia, are interlayered with the red being hematite. There's some iron properties for magnetite, of course, because it contains iron. You'll find interbedded chert layers and silica layers, and sometimes you'll get some other precious metals involved with banded iron formations. When iron oxidizes, it comes in contact with oxygen, and it forms a rust-like oxide, do not readily dissolve in water. So that iron has to drop out, in other words. When it happens, that will allow it to make thick blankets of iron at the bottom of the ocean. So bits only could have been made in water where free oxygen was available. That's important to note because these dudes right here, stromatolites, live in two really important places in the world today. The ones I have here in the Bahamas, and then the ones from Shark Bay, Australia. So as iron dissolutions out and deposits this thick quantities of it at the bottom of the ocean floor, it's only going to do it as long as there's iron readily available in the water to do so. Once we have precipitated all of it out and dilutioned it all out, the oxygen will then start to rust rock and eventually go up into our atmosphere, and create oxygenating atmosphere, which ultimately will lead to an ozone layer. So as free oxygen accumulates in the oceans, a waste product of stromatolites, which is exactly what happens today, it caused the precipitation of oxides and silica, which then form banded iron formations. This is going to continue until the iron in seawater is 100% depleted. So bottom line is we can't go turn the clock back and make more iron. What we got is what we got from the Paleoproterozoic and the Archean. And keep in mind the Paleoproterozoic gives us 92% of all of that oxygen. The first continental red beds are the first sandstones or shales that were caused by iron oxidations. And these deposits appear 1.8 billion years ago. Excellent test question, because that marks the time that we know the oxygen had free, or should I say the atmosphere had free oxygen enough to rust rocks. This corresponds to free oxygen in the Proterozoic atmosphere. This is so critically important to understanding the development of our first life. So stromatolites and outgassing from volcanoes are cranking out all this atmosphere oxygen, which is going to lead to the formation of our ozone layer. So test question, when did the ozone layer first come to be? And that's going to be somewhere during the Proterozoic, right at 1.8 billion years. So we know when we start seeing red rocks that we are getting oxygen in our atmosphere able to rust those rocks. Something else that happened in the Paleoproterozoic was glaciers. Tillites are very interesting rocks that look like this. They're simply a hodgepodge of rocks that are deposited by glaciers. We also see evidence of glacial striations, glacial polishing that happen to bedrock that is this age or older. So we find these kinds of deposits in Michigan, Wyoming, and Quebec, suggesting that North America had a substantial ice sheet of some sort, like a continental ice pack centered southwest of Hudson Bay. So we know that one came out of there in that region during the last ice age, so it seems to be a pretty good spot for glacier growth to occur. In the Neoproterozoic, glaciers are going to reappear on the planet, and we find evidence of worldwide glaciation on every continent minus one, Antarctica. And this dates somewhere between 900 and 600 million years ago. This corresponds to snowball Earth. So the glaciation didn't happen in just one big pulsation. It actually happened with 4 major episodes that are currently recognized during snowball Earth. So the actual growth extent of these glaciers are not known, and they did not all happen at the same time. So we've reached the point in the Proterozoic that we have to discuss one of the most important events that's going to set the stage for the rest of the course. Snowball Earth is a theory with some good, strong, compelling evidence that it occurred, not just in the form of glacial evidence, but also the aftermaths of what would happen as it melts. Let's talk about how it even formed. How would such a widespread global glacial event occur? First and foremost, it has to do with the supercontinent of Rodinia. So you learn that Rodinia came about 1.1 billion years ago, which would put it in the Neoproterozoic, at the beginning of the Neoproterozoic. And like all supercontinents, eventually they rift apart. Well, the rifting is going to be the answer to what happens to kind of melt the continent covered ice and the snow covered ice packs of the oceans. But let's talk about how we got the packs in the first place. As these continents were in a supercontinent position, they would have been exposed to vulnerable amounts of weathering. When rocks weather and make the deposition of new rocks, they will produce, or should I say, they actually absorb carbon dioxide and allow very little production of carbon dioxide to the atmosphere. So you can end up having a depletion of a necessary greenhouse gas in order to regulate global climate. That's certainly what happens here. On the flip side is, while you're weathering rocks, you should also see a global warming event where you get more CO2 into the atmosphere. That's what's going to happen to us when we finally get the oceans too acidic, and all that carbon-based limestone carbonate rock releases all that carbon back into the atmosphere. So they can have two effects, obviously, and in this case it had a very negative effect on global climate in terms of removing that necessary greenhouse gas for equitable conditions for life on Earth. So this would be one of our major challenges that multicellular life would face, and certainly prokaryotic life would face early on in its existence. Another problem with this process is that now we have the ice. When the ice becomes very reflective, which is an albedo issue for the Earth. Albedo simply refers to how well the Earth reflects and absorbs sunlight. So if you get a white surface like this, it'll reflect it and be unable to absorb more heat in our atmosphere. Plus, we have less greenhouse gases that will retain that heat in the atmosphere. So you get a double whammy there. So that's how snowball Earth came to be, and that's why it lasted for tens and tens of millions of years, actually closer to over 100 million years. And if you could imagine for an icebox of that nature for such a long duration of time, when it melted, it would have made a substantial change in sea level, which is exactly what's going to happen. And that's going to add to new habitat and great real estate for organisms to thrive and diversify very quickly. So at some point, the snowball Earth is going to have to melt. Realistically, it should have continued for hundreds and hundreds of millions of years, if not a billion years, if we didn't have a mechanism to stop it. Solar radiation could and will change over cycles with the sun, but probably not to melt this type of circumstance right here. Look at some of our Jovian planets in the outer solar system, and you'll see the exact same result. So something called the geochemical cycle played a role here, where the calcium carbonate in the ocean that had been generated as the ocean stores its carbon in rocks. So this is a powerful story in the magic of global warming and how important it is to look at our carbon reserves. So much of our carbon reserves, like 99.9% of all carbon, is constituted in carbonate-based rock. So as that rock is subducted into the mantle, it will literally be consumed and change the blending of those magmas and then come back up via volcanoes as carbon dioxide. So this process of ripping apart Rodinia is going to play a key role in producing the right circumstances to melt snowball Earth and set the stage for happier times, better real estate, and a chance to flourish for life after a frigid icebox for tens of millions of years. That leads us to the magic time in the Proterozoic history where sexual reproduction occurred. We know sexual reproduction actually occurred sometime starting in the Mesoproterozoic. And we have evidence of that. Banjamorpha is this animal right here, our first eukaryotic cell that could reproduce sexually. And imagine the challenges put in for sexual reproduction during snowball Earth. So if you are just given warmer conditions, better real estate, in other words, you have no competition for your space, you can just flourish. Imagine how quickly life is going to take off. And that is exactly what we see in the rock record. So in the Neoproterozoic, we're going to specify its time in just a minute. We're going to see this remarkable change after the melting of snowball Earth because sea level rises and it starts to cover parts of continents and creates our first lost sequence known as the Salk Sea that you learned about in transgressions and regressions. Our first eukaryotic cell was a kind of an interesting story. It had a symbiotic relationship with prokaryote cells, and they formed what's called an endosymbiotic relationship in which they formed a unit together. Ultimately, this would give rise through evolution to a multicellular organism who had very specialized functions in their cells. And that's what differentiates us from other eukaryotic cells and certainly prokaryotic cells. The fossil record does not explain how this happens, but it just gives evidence that it did happen. So we're going to look at some of those organisms that appear in the rock record in the Neoproterozoic that represent this important change that is going to occur in the Proterozoic. The best evidence is found in Ediacaran fauna. Ediacara is a place in southern Australia I tried to go there when I visited Australia and had really done some research on how to make it happen. But the long story short was it was going to take about a month by foot, and I would have hired or had to have hired an Aborigine to take me into Aboriginal lands, which also would have required a special research permit, visa, so forth. Obviously, just not worth the effort to do to see these fossils when you can go see them in a museum like the American Museum of Natural History or the Smithsonian in DC. But I still wish I could have gone, but it was just not a practical or safe venture to do so. So, a little crazy thing about these fossils, they are found in a quartzite. So, think about the parent rock of quartzite and that sandstone, and I'm going to not make light of this, it's actually kind of serious. There's a line in the sand, for real, between Precambrian and Cambrian aged rocks. The formation that's famous for containing these slightly metamorphosed sandstones that contain these fossils is called the Pound Formation. There's some members within there called the Ronsley, a few others, but the Pound Formation is what we're interested in talking about. So this process in these rocks gave us proof to answers that we knew to be true well decades before they were discovered. Before 1947, geologists already knew, they hypothesized there had to have been some fossils in Precambrian aged rocks. It wasn't just that we magically started the fossil record in the Cambrian period. So we knew the evidence was there even though we hadn't found it. So we were out looking for it, and lo and behold, they're discovered in southern Australia in the Ediacaran Hills. So Ediacara is also referred to as Vendian with a V. That's this word right here. So for a long time in the rock record, it was considered the last period of the Precambrian Eon of the Proterozoic. I also might point out, if you look at your time scale from geologic time, the one right before, the period right before Ediacaran is Cryogenian. That's important because cryo means ice, and that refers to snowball Earth. So just to kind of correlate the two, how they put together. So Ediacaran fauna is not just limited to South Australia. As a matter of fact, it's been found pretty much worldwide except on Antarctica. And 3 major localities in the world are the most famous. The one, Ediacara in South Australia, obviously. Then the White Sea outcrop that's found in Russia, and Mistaken Point in Newfoundland. So those are the 3 major locations, but not the only sites that contain these animals. So if you hear the term Ediacaran or Vendian, it's just referring to a time frame, not referring to an actual necessarily specific location. It will identify in the fossil description where those fossils were actually discovered. Ediacaran fauna are thought to represent 3 living phylums from today. First is Cnidaria, which would be corals like jellyfish and sea pens. Secondly, from Annelida, which is the segmented worm phylum. And then phylum Arthropoda, which is segmented animals like trilobites. But trilobites were not thought to have been alive at this time. We know that these fossils were widespread, so they were good index fossils. The difficulty and challenge for them is, how do they get preserved? We're talking about soft-bodied animals. They didn't have durable skeletons on the outsides of their bodies. So you would have to talk about optimal depositional environment conditions to bury these animals to where their impressions could be preserved and their casts could be preserved. Well, essentially, that's what happened. The first of these organisms we're going to discuss is Cyclomedusa. My personal favorite. I just think it's a cool looking animal. They could just literally be a little couple of tiny millimeters in size up to a meter, which is 3 feet wide. Most of the specimens that you'll see in famous museums are about 1 foot to 2, maybe 3 feet wide. So it had a very large range of size, interesting for it. We think it's related to a cnidarian, specifically a sea anemone, that it was a benthic polyp. So polyps will sit at the bottom of the ocean floor, have tentacles like this, and they will have a stinging nematocyst that allows them to sting something and bring it in and eat it. So these would have anchored themselves to the bottom of the ocean floor and been feeding through filter feeding mechanisms. This is a very common and very widespread Ediacaran fossil. Another famous Ediacaran fossil is Charnia. Here's what Charnia looks like. You can see it looks like a big giant leaf. Don't be deceived. That leafy body was attached to a disc-shaped holdfast, and a holdfast is a mechanism allowing an animal to anchor down to sediment. So it allowed it to attach to the bottom of the ocean floor. This is one of the largest Ediacaran fossils, reaching sizes of 1 meter long, so 3 feet long, filter feeding type of organisms. Charnia is most closely related to what we call living sea pens, which fall in phylum Cnidaria. They're very distantly related to modern day corals. We're found in Russia, in the White Sea location, Newfoundland, Mistaken Point, and even northern Siberia. Sprigina is actually named after the guy who discovered Ediacaran fossils to begin with. This is a fascinating guy. He looks like a big giant worm. He's not. He is related to an arthropod, very segmented, has a distinctive front and end to him with the segmented body in between. There were no hard parts like we would see in something like a trilobite, so we have no idea if he had appendages, how he moved. I mean, more than likely, it would suggest that he did, but we just don't have a fossil record of that. Keep in mind, the preservation of these organisms is remarkable at best, since they were soft-bodied to have any evidence that they lived. That goes back to our fossil lecture discussion. Remember all those animals that haven't been preserved? There's likely a lot more in this category that we've never discovered or will never even find remains of, which is sad, but nevertheless, when we do find one, it gives us a glimpse into what's going on in geologic past. Tribachidium is another famous fossil that's found from Ediacaran fauna. It's kind of a funny looking animal. It's a disc, kind of a round shape animal that distinctively has a 3-part symmetry pattern in the middle of it. There's question mark. Is it related to a cnidarian, like a coral or a sea anemone, or is it related to an echinoderm? Really, there's not good evidence to be connected 100% to either one. There's proof on both sides, but what we do know is that it lived on the bottom of the ocean floor. So an interesting animal, commonly seen in most all Ediacaran fauna assemblages. Kimberella is another interesting but yet controversial Ediacaran fauna. It's about 3 centimeters across in its width, which would be similar to what we might see shelly animals today. An important specimen was found in Russia that had very deep depressions that were embedded in the rock layer underneath it, which was siltstones and softer rock. That would be similar to a soul mark that you might have learned about in physical. So when you get one stone that's harder to another and it leaves an impression on the stone beneath it or above it, that's called a soul mark. And these fossils are found in that very thing. So you're not finding the hard-bodied evidence of it, but what we do see is suggestions that it could have had some type of a tougher shell coating, not suggesting that it was a mollusk or a brachiopod, but something similar maybe evolving towards that direction. So Kimberella is kind of the mystery marker of the Ediacaran fauna. Could it not be something that was hard-bodied? You would think if it was, we'd have a lot more samples of it. So keep that in mind, that this may just be a special fossil that we have, a very special specimen that we have in the rock record. Nevertheless, Kimberella is a famous Ediacaran fauna. Sometimes you'll read about fossils that predate Ediacaran fauna. So that would be stuff older than 650 million years in age. So we're talking about stuff 700 to literally up to 900 million years of age. Well, it appears the only things that were alive at that time were worms, so annelidas. Now, the worm burrows that you would find in those very hundreds of millions of years old rocks are not going to look nearly as nice and well preserved as these right here. Nevertheless, there's evidence of those, especially in China. China has the most incredible, oldest worm burrows that we have found to date. Interestingly enough, though, there are substantial worm burrows that are found about 2,000 meters, which would be 6,000 feet, beneath the famous Ediacaran Pound Formation. So we've got evidence of life, but that's primitive life. And as we see in the rock record regularly, the theme is going from primitive to more complex, which is exactly what we're seeing happening here. We can't talk about the Proterozoic without talking about the value it adds to the economy. Mineral resources in a number of ways have been gathered from Proterozoic rocks, both from Paleoproterozoic and Neoproterozoic, really from all three sections. But let's focus first on Paleoproterozoic. 92% of all the world's banded iron formation comes from Paleoproterozoic rock. That's a pretty impressive amount right there. Interesting to understand that the United States ranks in the top 10 countries of iron-producing countries from banded iron formations of this age. There's another place in Canada that has the Sudbury Mining District, famous for producing nickel and platinum. Platinum is extremely valuable and durable metal resource. The Bushveld complex of South Africa also contains platinum and chromium that's utilized and extracted for economic gain. Hydrocarbons even exist in China and Siberia, where they've been rifting apart, that are in Proterozoic aged rocks. That's interesting because hydrocarbons must come from some kind of fossil fuel. So that means early fossils were even capable of producing the right circumstances to make hydrocarbons. The Dunton pegmatite in Maine contains a very precious utilized mineral called tourmaline. The Harney Peak granite, of which you're seeing in this photo to the right, which is found in Black Hills, South Dakota, right where Mount Rushmore is located, has a number of precious metals, gemstones, and then very useful granite that is very strong and tough, that dates back to 1.7 billion years in age. So we're going to take a look at this particular outcrop and explain its significance. So I'd like you to look at this for a minute. There's not a person that doesn't recognize that's an American, the faces of the 4 presidents of Mount Rushmore. A really fun, interesting history of how did it get there. I've been there multiple times. It's right outside of Rapid City. It is off of a famous highway that I showed you a picture from in the last slide called Needles Highway. A great, beautiful drive right near Custer State Park. Great animals, by the way. And lots of famous movies have been filmed in that area. The last scenes of Dances with Wolves was filmed there. Of course, some of the famous treasure hunting movies that you might have seen Nicolas Cage in, where the last one was filmed there that he made. And what's famous about this place is the 14 years that it took to build it. So you have to put yourself back in the Depression. So in 1927, all the way through 14 years later in 1941, almost 400 people, men, women, and children, were responsible for building this particular structure. So how did they do it? Because this is a hard granite, very durable, low differential weathering rock. So it's a wise choice to build a national monument in. The average person thinks this is built out of limestone or marble. It is a granite outcrop, Precambrian, Proterozoic to be exact. So here's what happened. Some dikes came up through the subsurface as we were making Rodinia. And this is part of that process right here, is evidence of our ancient supercontinent. And these magmatic plumes created dikes and sills that oozed up to the surface and created plutonic structures of what you're seeing right here, which is the remnants of a volcanic neck. So these people, these almost 400 men and women, worked for $8 a day. $8 a day, which was good money back in the Depression. Not without its risks, though. To even clock in, they had to hike up 700 stairs to get to the very top where they could clock in to get paid for the day. And then they would have these self-propelled, what I would call seats that they would work up and down with onto the faces. To make sure they didn't bang into the faces, they had children at the top who were call boys, and literally that was their name, call boys, that actually called down to let them know where the safe places were that they could be pulling up and down for. They blasted with dynamite out these walls, and so that's the unsafe part of this. So they'd have to pulley themselves up to the top, dynamite, and go back down. And so the call boys became very important for the safety of these men and women who were doing all this work. Not a single person died carving Mount Rushmore, which is a pretty phenomenal feat. More phenomenal to me is the fact that the rock's even there for us to have built these magnificent faces into that represent the founding fathers of our country, which I think is very appropriate with the type of rock that they built it on. A strong foundation rock, basement rock, Precambrian rock. So more to come, and I will see you at the next series of lectures. Bye.